So let's begin. Good afternoon. We have seen several applications of the fix command and the compute command for calculating, say, radial distribution functions, the velocities and things like that, and then also averaged them over specific time intervals and plotted them in previous two classes. Another important aspect that we can generally obtain from molecular dynamics simulations is the diffusion coefficient or the self-diffusion coefficient of the atoms. So this does not require any explicit chemical potential or mass gradient to be provided to the system to see the atoms move. Okay, this is just qualitative measure of how much the atoms may actually be diffusing in the system over a given period of time. So when you want to compare systems, then it gives you a good indication as to how whether atoms in krypton are moving faster or whether atoms in argon are moving faster and things like that. So what we have to compute is what is referred to as the mean squared displacement of the atoms in the system. And if you plot the mean squared displacement of the atoms over time, and the slope of the mean squared displacement atom is basically proportional to actually the diffusion coefficient. Okay, so we will see a the actual theory that tells us this, that the mean squared displacement is proportional to the diffusion coefficient, is comes very much later in statistical mechanics. So we will have to know a lot of background in order to actually understand exactly why it turns out that way. So instead of going through all those details, I have just put forth some simple qualitative derivation which actually gives us the same result for a one-dimensional system, and then we will extend it to three-dimensional systems. Okay, so if you consider one-dimensional diffusion, so if you have say n is basically the total number of atoms that is present per unit volume at a particular point in space, say x, at a given time t, then you know its distribution is actually governed by this differential equation. The rate of change of n with respect to t is diffusion coefficient times dou square n by dou x square. So if at time t equal to 0, we have certain n0 number of atoms placed right at the origin, and then if you let the atoms diffuse, then they will eventually, the concentration at the origin will start decreasing and they will start spreading out. Like for example, a drop of ink that's dropped on a plate of say water, right? If you drop a drop of ink right at the center, it will start spreading out. So if you solve the differential equation for this boundary condition or initial condition, it so happens to have this particular solution where the evolution of n with respect to time is nothing but n naught times some exponential minus x square type of function, which is basically a Gaussian function, right? So initially it will be peaked like this, and as time progresses, the peak from its narrow appearance will start broadening out. Okay, so at any time t greater than 0, the second moment of this distribution, so basically x square times n of x dx divided by n naught is basically nothing but the square of the mean of the square of the distance that the particular atom has actually traveled from its initial position. So this is a one-dimensional expression. So if you actually plug the value of n of x into this expression 34 here and solve, you happen to get the mean square displacement is the average mean square displacement is actually equal to 2 times dt. Then of course this expression is actually valid for extremely long periods of time, and the above equation is and if you look at the 3D version of it, all you have to do is divide by 6. So in the limit of extremely large t, the mean square displacement of the atoms divided by 6t is actually the diffusion coefficient of the atoms. So here this is x of t. So basically, since we are talking only about one-dimensional diffusion, so r of t minus r of 0 the whole square averaged over, say, all the atoms in the system is basically nothing but the square of the distance that the particular atom has traveled at time t from its initial configuration averaged over all the atoms in the system. So it is actually a function, this expression here is actually a function of time. right? The mean square displacement is actually a function of time. And if you divide it by 60, so here it is 2 dt. So if it is going to be a 3-dimensional system, it happens to be the exact expression for a 2-dimensional system is 2 times dt. So if n is equal to 3, it happens to be 6 times dt. So you get this expression for the diffusion, self-diffusion coefficient of a system. So in molecular dynamics, a more convenient form is used where you say 1 by 6n and you plot the mean square displacement. So you basically calculate the current position of an atom at time t from its initial position, right? You calculate the distance that it has traveled, square it, do this for all the atoms in the system. Basic assumption is that all the atoms are essentially the same atoms, so they would behave essentially the same way, and you get better statistics, right? And once you average it over all the atoms in the system, you take the slope of this mean square displacement versus time curve and divide it by 6 times n. You essentially get the, this is for one atom, and then summed over all the atoms divided by n, which is essentially averaged over all the atoms divided by 6 of that particular slope will essentially give you the diffusion coefficient. Okay, so this is a very brief and a rough overview of how this expression might have come about. The details, you can take a look at some statistical mechanics book and you will find it there. But this part of the course is not about teaching you how to derive this, but to see how we can calculate the mean square displacement with LAMMPS. Okay, so this is done in exercise 11. This is exactly the same input file as the previous exercise, which is 10. Okay, and the only difference that I have done is, after relaxing the system completely, say fix 1 all NVE, run 10,000 was the last NVE, and after that we did another NVE fix in order to compute the radial distribution function. But now I am going to compute the mean square displacement. So one of the things that happens is we are going to have to print out the mean square displacement. Okay, so I would like the code or the script to print out only the mean square displacement information in a separate file and not along with everything else, because it becomes cumbersome for me to open that file and delete all the previous steps and look at only what I want. So what I do is I just say log msd file.txt. So from this instant on, it will start printing out information in a new file. So I say compute msdisp all msd. Msd is basically the msd, and com is equal to s basically specifies that when it calculates the velocities, it removes this velocity of the centroid of the system, if at all there is any, right? So that's what it does. So and then I am running the NVE fix right here. So all these calculations are done after these variables have been defined. So this mean square displacement is actually computed over this NVE right here. Okay, and I say thermostyle and I give a variable. I'll tell you what this variable is in a second, and then I print out C underscore ms disp1, disp2 and disp3 and disp4, which is basically the mean square displacement along the x, the y, the z and the magnitude of the mean square displacements. Okay, what I have done here is, since this time here is not actually going to start from 0, but it is going to start from finite value, because I have run a lot of simulation about this, I just define a simple calculation here where I say tt is equal to time, and then say my mtt is equal to time plus $tt, which essentially subtracts the current time from the previous time, and hence this variable, when it prints out, it will start printing it out from 0. So then it is nice to plot this entire thing. Another things that you should notice is that when I am trying to do this mean square displacement, I am running it over at least 2 or 3 orders of magnitude more number of time steps than what I did for other simulations. So it might have reached equilibrium, but if I want to look at the region in the MSD versus T plot where the diffusion coefficient is actually proportional to the time, then I'll have to wait long enough for this diffusion for this relationship to actually show up. Okay, so yeah, yeah,
In this case, you declare TT equals time and MTT equal to time minus dollar.
yeah.
So in this case, like how does it execute? Because like every time when you say like execute line 48 and then line 49, it's gonna give 0, right?
No, TT equals time, and then I said dollar $TT at this particular instant of time. TT is going to have the value of time that it currently, whatever the value of time it is currently, right? Then when I say use the word, when I use time, it is actually the current time minus dollar $TT. So always the time that was stored in TT will actually be used.
So, but that is the same as 48. For 48's declaration, 48.
You're not printing TT in thermostat, so it will never be calculated.
You are only calculating V minus MTT. No, MTT is the only thing that is being calculated. So it will never print out. TT has a constant value now. So if you look at the file, I don't know where the file is. It looks like this, and this is the first column is basically the time, and it's going till about 20,000 what? 20,000 picoseconds is the time, right? It's huge, right? 20,000 picoseconds is a very, very long time, but you need that time in order to actually see the diffusive regime and be able to calculate the diffusion coefficient. So when you do this, this is how it looks. So in this region at extremely small times, so this plot shows two things. One is actually the continuous looking line, which is basically from the simulation, and then the thing that's marked, which is basically a linear fit over this. So if you look at it very, very carefully here, the fit is actually not so good. Okay, this starred asterisk mark is basically the linear fit, whereas it starts off a little bit flat. So you need to make sure that you're running your MSD simulations for long. Of course, it doesn't have to be such a long time for this system. This is just for illustration purposes, and it's only 4,000 atoms, and this simulation completes within a reasonable time frame. But when you're looking at larger systems, then you have to be careful as to how long you want to run this simulation. So once you run the simulation, we can obtain, so I'm not able to open MATLAB, you can actually perform the calculation and check the value of, so this MSD, not only does it also, the compute command MSD, it also averages it over all the atoms. Okay, so one of the things that you do not need to do is, after calculating the MSD, you just need to calculate the slope and divide it by 6. You do not need to divide it by the total number of atoms that's present in the system. So I have some caption here, is just not turning out. I did the calculation and I compared it to the paper that I just shared with you. Let me show you the values here. So what I get is, I get a value of slope which is about 1.1513 e to the 4. I just have to divide it by 6 and I get a diffusion coefficient of about 1.9188 times 10 to the 3 angstrom per picosecond, angstrom square per picosecond, which is approximately equal to 0.19188 e to the minus 4 meter square per second. So if you look at the argon paper, I've shared this paper also with you, right? The argon paper. If you look right here, they basically made the exact same plot. This is exactly what we have for 300 Kelvin, and that's a very small region where it is nonlinear. Actually, this is maybe a couple of picoseconds actually. So you should make sure that you're running it a reasonably long time to make sure that you see the diffusive regime. And the value that they get is about 0.1890 e to the minus 4, which is quite close to what we have got, and it's compared in this table as well. Okay, so So you can try to do this for krypton and other noble gases. And in this paper, there are also techniques that's given as to how you can actually simulate the mixture of gases, a combination of both argon, krypton, and so on. So these things can also, this paper can also teach you how to do that. Okay, it should not be very complicated to understand how to model the behavior of a mixture of these ideal gases. So please take a look at this article and try to simulate as many plots as you can from this paper. It's a very good learning experience. So now there are the only interatomic potential that we have looked at so far is basically the Lennard-Jones potential, and it is a pair potential. And many other potentials also, although they don't usually model ideal gases, like for example solids, they are also pair potentials, and apparently they do very good jobs. Okay, let us take for example one type of potential which is called as the Born-Huggins-Meyer potential. Okay, it is useful in ionic crystals. So ionic crystals, what happens is that the bonding that is existing between the atoms is essentially ionic, and the long range interaction between the charged ions is so effective that it is the only part that is effectively important by and large. And then you just need to have some other short range potential which is a pair potential, which will just take care of the electron repulsion that is existing between the atoms. So the Born potential, the particular potential looks like this, and it is generally used to model ionic crystals where you have mixture of alkali or alkali earth metals with group 6, group 7. So basically oxygen, sulfur, group 6, group 7, chlorine, and all those halogens basically. Okay. So this potential looks like this. So you have a part which takes care of Coulombic interactions, and another part which is basically a short term interaction existing between the atoms. Okay. Now this part contains both repulsion and attraction depending upon the state of charges between the interacting ions, whereas this is exclusively repulsion. Okay. So here you have capital Z is basically the atomic number, small z is basically the number of electrons in the outermost shell of that particular atom, E is the electronic charge, sigma, A and rho are the fitting parameters and depend on the specific ionic species that you are talking about. So for sodium there will be something. Okay. So one of the important aspects that is that makes this potential a little bit difficult is the following. So this part, the part that is concerned with the repulsion, short range repulsion, is pretty straightforward, and there is no special treatment that is actually required in order to evaluate this. Okay, this is just rapidly decreasing potential, right? And it is also exponentially decaying, which means that the potentials go to zero quite fast, right? So if you are sitting on an atom and trying to evaluate the energy due to some other atom, then you only need to consider so much distance from that atom when you are calculating this portion of the interatomic potential, because it's exponentially decaying. However, this one is not like that. This is actually having a 1 over r decay, right? It's having a 1 over r decay, which is much slower than this. And as you increase r, as you go far away from a given atom, the total number of atoms that you have to basically consider increases as r square, right? So this component of the interatomic potential is extremely tricky, and the cutoff that you have to give for this interatomic potential and this interatomic potential can actually be different, right? Now this computation of this is actually quite challenging, and people have developed a lot of smart ways to actually see how to compute this, so that you can find the cutoff radius in such a way that within that cutoff radius this term should actually converge to some value, right? But this actually converges over a very large distance. So we are not going to talk about how that is done inside LAMMPS. Okay, I will just say that whenever you are using ionic crystals, you have to make sure that the cutoff for this is large enough that your energies are going to converge. Okay, so there may be some trial and error that might be important for you to do if you are working with new systems in order to figure that out. Is that okay? So that's with respect to the potential, and these are of course fit to reproduce some property of the material. Now, whatever we saw was a two-body potential. There are many other two-body potentials. All of them have different names and different parameters to determine depending upon the problem, but they are all fundamentally the same thing. There is not anything different. Now, when you talk about the next potential, so when I talk about two-body, three-body, I would like to point out to this expression that we have seen earlier. This expression that we have seen earlier, this is the reference, and this is the two-body term, this is the three-body term, and so on, right? So three-body term essentially depends on three atoms, so the distance between alpha beta, beta gamma, and alpha gamma, right? Four-body means even more, right, and so on. So the class of pair potentials comes under this, and if you have additional potential, the three-body potential comes into picture, and one example of that is the Stillinger-Weber potential, which is used to model solids with a strong covalent bonds, like for example carbon, germanium, silicon. Okay, diamond structures in these materials are very often modeled using this Stillinger-Weber potential. The potential turns out to be quite complicated and it results in about 7 to 8 fitting parameters which you have to find in order to match experimental results. So it consists of a two-body term plus a 3. So V suffix alpha beta is basically the two-body term in that expression that I just showed you before. V suffix alpha beta gamma is basically the three-body term, and it depends on all these, it depends on the distance between each of these individual atoms. So F2, which is basically the two-body term, simply depends upon the position and this power P, power Q, which looks just like your Lennard-Jones potential, right, except that it is P and Q are not 12 and 6, and you have this additional exponential R bar minus A term creeping in, and as long as R bar is less than A, then you have to have this potential, otherwise it's 0, and the three-body term is the sum of G1, G2 and G3, and each of this is depending on alpha beta, alpha gamma, whereas this one depends on, it's a function, there is a functional form, but in that functional form you need to substitute the distances between alpha beta, alpha gamma, and then gamma beta, alpha beta, and so on, right? So G1 is just one functional form which looks something like that. So G1, each G depends on only alpha beta and alpha gamma, two distances and one angle. So if you are sitting on alpha, the distance between alpha beta and alpha gamma, and with this as a center, the angle that is existing between them is basically theta superfix beta alpha gamma. So how this needs to be read is, I am sitting on atom alpha, I am drawing a vector from alpha to beta, alpha to gamma, and measuring the corresponding distance in between, corresponding angle in between. Okay. So these are just general functions, and for silicon, diamond silicon, this potential is used a lot, and the form of the interatomic potential looks like this. So there is additional parameters here, lambda, and then gamma, and then you have a cos theta plus 1 by 3 the whole square term. So if you look at silicon, diamond silicon, if you know the structure of it carefully, it basically forms a tetrahedron, right? There will be a silicon, and then there is a silicon on top, and then there is a silicon that is right here forming a tetrahedron, and the angle between this and this would be 109.5 degrees, right? The angle of the tetrahedron angle. That is the cos of that angle is actually 1 by 3. So this term here is basically forcing that angle that is existing between these bonds to actually be 109.47 degrees. Okay. So This potential will have about 8 parameters, which are again obtained by fitting data to match the material properties, right? Okay. So we will try to see if we can do some examples for Stillinger-Weber potential, and later on we will look at other types of potentials also. Now the question is it always, yes?
Why is there a dependence on?
So the question now is it always possible for us to actually have potentials by just adding 4 body terms and 5 body terms and so on? So it so happens that people have actually stopped with 3 body terms, and there are very few works which actually consider 4 body interactions in materials. Okay. So the next thing that people developed was, for many systems it is not sufficient for us to actually just consider or cut off or truncate off the potential at 2 body or 3 body. The other terms also are important, but they happen to make things a little bit complicated, simply because now once you have 4 body terms, you will have to consider the distances between alpha, beta, beta, gamma, gamma, delta, and all the combinations that are there. It becomes very, very cumbersome. So they developed a potential that is referred to as functionals, functional potentials. So we will look at that in a little bit, give you a brief introduction to that, and describe 2 potentials that is associated as functionals. Basically the Tersov potential and the embedded atom potential are these functionals. So we will try to do some examples based on them as well. Okay.